everybody, Mrs. Pesic here. We are finishing our look at section 3.2 on logarithms. So if we look at the graph of f of x equaling log x, and we can pull up our calculator here, and let me just go to a graphs page. And if I'm going to graph log x, that's base 10, right? Because we didn't say a base. So I'm just going to say log x. There's the graph of the logarithmic function. All right, I can just kind of drag this a little bit this way so we can see it a little bit better. And then if I want to compare this graph to some of these other, by the way, the characteristics for logarithmic graphs are on page 212, so I strongly encourage you to take a look at those characteristics. If we're going to compare the graph of log to the base 3 of x, so I guess let's try log to the base 3 of x here instead. So I'm going to add a new page, and I'm doing log to the base 3 of x. Okay, so there's log to the base 3 of x, but now what if we had log to the base 3 of x minus 1? What kind of transformation would that be? So if I try and do that, I push tab, and I'm going to do log to the base 3 of x, and then outside of that parentheses I want a minus 1. Well, that whole graph has just been shifted down 1. So we can say this is a shift down 1. And then if we look at this next one here, this one is log to the base 3 of x plus 2. So let's try that one. That's x plus 2 in the parentheses. So I'm pushing tab, and I want control log to the base 3 of x plus 2, and that one is being shifted 2 units to the left. So that's what we can write for this one. This is a shift left 2. All right, so we can talk about the natural log function. Remember, we have the common log is base 10, but the natural log function is going to be the inverse of the natural exponential function. You remember the natural exponential function was the one that had base e. So if we have this function, log to the base e of x, that's going to be the inverse of this exponential function. But log to the base e of x is used so often that it has its own name. All right, it's the natural log function, and we have its own way of writing it, and that would be ln of x. That is not an I, that's an ln of x. And that's how we say it. We say ln of x. All right, it's read ln of x, I guess, just like that. All right, and so we can write it y equals ln of x, and we could write that same equation as x equals e to the y. Those are equivalent equations. So let's test this out with our calculator, making sure we can find the ln button on our calculator. What if I want ln of x plus 1, but I want to plug this in for x? So I want ln of 73.25 plus 1. Let's do this on our calculator. So log to the base, this log to the base e, so ln, but I'm going to go to a, escape. I want to go to a calculator page, and I want to do ln, that's control and the e to the x button, and I wanted 73.25, I believe. Yep, and then I want a plus 1 after that. So I got to get out of the parentheses and a plus 1, and I'm getting 5.29 as my answer. Let's see if we agree with that. Yeah, about 5.29. All right, let's try ln of negative 2. Let's skip down to letter C. If I want ln of negative 2, and I try this on my calculator, control ln negative 2 with the plus 1 on the outside, I'm getting that same warning message saying, hey, you're not allowed to plug negative numbers into logarithms. So this number right here must be greater than 0. I could say must be a positive number. All right. Okay. So we you can try the rest of those if you would like. Let's move on. Let's talk about the properties of natural logarithms. These properties are just like the properties that we talked about in class. So ln of 1 is equal to what? Well, remember, ln of 1 means log to the base e of 1. So that means e raised to what power gives me 1? Well, e to the 0 power will equal 1. So that's why ln of 1 is always equal to 0. What about ln of e? One number 2. ln of e means log to the base e of e. Well, what's that going to equal? Well, this is really saying e raised to what power gives me e? And the answer would be e to the first power is equal to e, which is why anytime you see ln of e, it's always equal to 1. All right, and then we have this third property here that says ln of e to the x is equal to x. Remember, we talked about this, that exponent can come down in front, and that would be like x times ln of e. All right, but we just talked about ln of e. We know ln of e is equal to 1. So that's like x times 1, which is equal to x. All right, and we did talk in class about why is e raised to the ln of x going to have to equal x. Remember, this is in exponential form, so if I want to see what's happening or prove that this is true, I could just rewrite it in log form. So if I do that, I can write this as log to the base what of what equals what. And in this case, I can say log to the base e of x is equal to ln of x. You know how to rewrite these. And log to the base e of x is the same as ln of x. So I get ln of x equals ln of x. And then the last property is the one that really is the one-to-one property that says if you've got ln of something equal to ln of something else, then those two somethings have to be equal to each other. So here's some practice problems for these properties. So if I want ln of e to the 1/3, again, think of this 1/3, this power can come down in front. So this is going to be 1/3 times ln of e. And ln of e, that means log to the base e of e. So I've got 1/3 times log to the base e of e. And this is saying e raised to what power gives me e? That's equal to 1. So I really have 1/3 times 1, which is 1/3. How about letter B here? I've got ln of e over 6. Well, we know ln of e, again, that's log to the base e of e divided by 6. But log to the base e of e is equal to 1. So I get 1/6 as my answer here. And let's take a look at letter C. For this one, it's e raised to the ln of 8. And let's say you forget, I don't know what that's supposed to be, but this is in exponential form, so I could rewrite it in log form. Log to the base what of what equals what? Well, this base e is going to go right here, so it's log to the base e of this box. I don't know what's supposed to be in this box, but I know that this ln of 8 has got to be over here. So I get log to the base e of box equals equals ln of 8. Well, log to the base e means ln, so I've got ln of box equals ln of 8. Now that tells me that what goes in the box must be an 8. So that's why the answer for this is equal to 8. Do you have to show all these steps? No, you just need to know that e raised to the ln of 8 is going to always equal 8. All right, last one here, 15 times ln of 1. What was that ln of 1 again? That's log to the base e of 1, which is really saying e raised to what power gives me 1? Well, that would have to be e to the 0 gives me 1. That means ln of 1 is really just a fancy way of writing 0. So we're going to write this as 15 times 0, which is 0. All right, let's talk about the domain for each of these functions. If I want to find the domain for the function ln of x minus 2, remember that whatever we plug into an ln function or any logarithmic function has to be positive. So x minus 2 has got to be greater than 0. All right, and so if I add 2 to both sides, I get x is greater than 2, and that's going to be my domain. So I could write it as, whoops, I don't want a bracket, I want a parentheses. The domain would be parentheses 2 to positive infinity. Let's take a look at letter B. This time we're trying to find the domain of ln of 2 minus x. This 2 minus x better be greater than 0, so 2 minus x greater than 0. I can subtract 2 from both sides. I get negative x is greater than negative 2. And if I divide both sides by a negative 1, I have to remember to switch the direction of the inequality. So I'm going to have x is less than positive 2. So that means my domain, I'm going to write my domain for this one, is going to be negative infinity to 2 parentheses, because I don't want to include the 2. What about this one? ln of x squared. Well, this x squared has got to be greater than 0. And that sounds like x has to be greater than 0, right? X has to be greater than 0, right? Well, let's think about that, and let's actually graph this one to look at what the domain is going to be. If I want to graph ln of x squared, get rid of that writing, let's go to a graphs page, and I'm going to graph ln of x squared. Look at that beautiful looking graph. Well, that graph is great, and if I pull up a table, Control T, notice what's happening when x equals 0, we get undefined. But everything is defined other than that, because remember, what you plug into an ln has to be positive, not just 0, not just non-negative. So in this case, I think we're going to have to say that the domain here is x greater than 0 or x less than 0. So in this case, we could say, hey, this is negative infinity to positive infinity, but x cannot equal 0. Or even better, in interval notation, we could say negative infinity to 0 with a parentheses, union with parentheses 0 to positive infinity. That's supposed to be an infinity sign. Okay, so that's that one. All right, that brings up this example. Students in a math class were given an exam and then retested monthly with an equivalent exam. The average scores for the class are given by the human memory model f of t equals 78 minus 17 times log of t plus 1, where t is between 0 and 12, all right, and t is the time in months. All right, so what was the average score on the original exam? That means when t is equal to 0. All right, well, we can plug in 0 for t, and we'll get 78 minus 17 times log of 0 plus 1. All right, can I do 78 minus 17? No, I cannot, because order of operations says I would need to do this multiplication first. So I need to basically take 17 times log of 1, right, minus, and take that, subtract it from 78. Let's actually do this on our calculator, and for that matter, let's actually just graph this and go from there. So I want 78 minus 17, going to a new graphs page. I want 78 minus 17 times, and I want log of, this is ln, right? No, it's not. It's actually common log, base 10. So I want log base 10 of, and it was x plus 1, I believe. Yes, it was. And I'm not using t plus 1, of course. I'm using x plus 1. And so I push enter, and I'm not seeing anything. Well, let's play around with the window, Control Dock. If I go to, oh, that's not what I wanted to do. Back up. Okay, here I am, and I'm going to do menu. That's what I want to do. Window zoom, window settings. Now, they told us that this is only good for 0 to 12 months. All right, and I know the minimum score on this exam has got to be like 0. You can't get a negative number on an exam. But the maximum would be, I guess, a student could get 100% on an exam. There's our graph. So that's what the graph looks like, and it sure looks like the time at which a student loses the most as far as scores are concerned, would be right in the initial, month or so, and then it kind of levels off. I mean, they're still losing what they remember from the test. All right, so how are we going to answer these follow-up questions? So if I want to know what about t equals 0, going back to my graph, I can just do menu, trace, graph trace, and type in 0, and it's telling me 78. So initially they get a 78% on the exam, at least that was the average. All right, and then if we go on and we try what was the average score after 3 months, then going here we can just type in 3, and it tells us the average score after 3 months was down to a 67.8. So they really already lost about 10 percentage points on average. All right, and then what else? What was the average score after 11 months? So I can just type in 11, and I'm getting 59.7. Of course, you could do the same thing pulling up a table, but I just chose to use the trace button. But as you can see, as time goes on, you start losing what you have learned. You don't remember all that much of what you learned. Okay, so that's what the human memory model is all about. All right, and that's it for this video. Thanks so much for watching.